This video looks at implicit differentiation, which is used to find gradients of functions where it's not of the form y equals, but some function of y equals. Now this has got exponentials in, and we know that generally if we have y equals e to the ax, then dy by dx is a e to the power of ax. And I will now use this rule to differentiate this function here. Now e to the 2y differentiates to 2 lots of e to the 2y, but because it's with respect to x, the whole function, I must times by dy by dx. So this is the underlying principle of implicit differentiation. So when I differentiate with respect to y, I differentiate as normal, so 2 e to the 2y, but times by dy by dx. Then if I now differentiate the right hand side, 5 differentiates to 0, and this part, minus e to the power of minus x, I times by minus 1, so it becomes plus e to the power of minus x. So dy by dx just equals e to the power of minus x all over 2e to the power of 2y. I divide by 2e to the power of 2y. Now, I want to find the gradient at the point 0, ln2. So if I sub in these two values, I get e to the power of 0 all over 2e to the 2 ln 2. So I've replaced y by ln2. Now this will quite easily simplify. E to the power of 0 is 1. There's a 2 here. Now if I raise 2 as a power, I get e ln 2 to the power of 2. So the 2 next to the ln can be raised as a power. Now I've got this, the e and the ln will cancel out because they're inverse functions. So I get 1 over 2, lots of, they cancel out, 2 squared. Now 2 squared is 4, 2 times 4 is 8, so the gradient at this coordinate is 1 over 8. So again, the key points here is that when I differentiate with respect to x, in this case, when the function of order y, I must times by dy by dx. That is called the chain rule. Further down, e and ln are inverse functions, so they cancel off to produce a times 2 squared. And also, when you've got e to the a ln, then raise that number there as a power within the function to allow e and ln to cancel off.